instead of coding everything in zeros and one and sending it to a CPU or a GPU, why not make physical neurons, layers of physical artificial neurons, and interconnect them directly with some kind of synapses that are really in between the neurons.
This is Brain Inspired.
Hello, good people. Welcome to the Spintronic Neuromorphic Nano-Oscillator Spectacular! Actually, I am excited because it's the first brain-inspired episode about neuromorphics, and I hope it's the first of many because I really enjoyed it. So we have talked plenty on this show about neural networks, deep learning, recurrent neural networks, and sundries. So the current way of running neural networks is you fire up your digital computer, you open your favorite statistics software program like Python, and you spend what seems like 10 days figuring out which of the newest hot machine learning packages to use, and you spend another 10 days learning how to code for that package, and then 4 years or so coding your particular network with your particular data, and of course, by then, you learn that your new hot machine learning package is now the senile guy in the room. And there's another new hot one to learn. Anyway, you run your network on a digital computer. And that's fine, but it has some drawbacks, like it's energetically inefficient. And as neural networks continue to scale up in size and parameters, their energy consumption will become problematic. So a solution to this is to change the hardware that we run neural nets on. Change the computer chips themselves to resemble a more brain-like architecture. Enter folks like Julie Grollier, with whom I speak today. So Julie is a research director in a lab under both Thales, which is a large French electronics company, and the National Center for Scientific Research, also a huge institution that sponsors a lot of research. Julie and I talk about neuromorphics in general and how they differ from current computer chips. We dive into her nanoscale hardware implementation of a neural network that uses the properties of electron spin, magnetic materials. I think there's some magic in there. Anyway, we talk about how it all works and how the network learns as well as current neural networks, at least thus far on a small scale that we talk about. So you can follow Julie on Twitter. She is at Julie_Grollier, Grollier. Her website has lots of nice introductions to the concepts and terms that we use. And she's given a TED Talk on this topic, and I'll link to all that and the rest of what we discuss in the show notes at braininspired.co/podcast/19. If you would like to help keep this show running and ad-free, I despise advertisements on podcasts, consider supporting it for a measly $2 or $4 per month. Go to braininspired.co and click the red Patreon button there. All right, thank you for listening. Thank you for your support. And here's our conversation. Julie Grollier, welcome. Thank you for being on the show.
Hi. Thank you very much. I enjoy your podcast very much. So I was very happy when you invited me.
Oh, thank you. That's very kind of you. Well, this is cause for celebration because this is the first episode in which we're going to talk about neuromorphics. So let's celebrate.
Cheers.
Cheers, yeah, all the way across the continent. So, Julie, you are in France right now, and I think you're in France, right?
Yeah, I am.
Okay. So you're a researcher director in the CNRS Thales lab in France. Is that how you pronounce Thales?
Yeah, perfect.
Oh, great. So you do work on bio-inspired computing, among other things, and you seem to be interested in saving the world. Is that right?
Well, if I can contribute a little bit.
Oh, that's modest as well. Very nice. Okay, so the first neural networks that were created really were perceptrons from Frank Rosenblatt. And they were built out of hardware. And I recently had Terry Sejnowski on the show, and he was telling me that he actually built one of those original perceptrons just by reading that original perceptron paper. He went and got the supplies and built himself one, using his own hardware. But these days, we run deep neural networks and machine learning algorithms on software on digital computers. And we build these networks now using Python, right? Machine learning packages.
Yeah, absolutely.
But you are back to working on building these things out of hardware. So let's just kind of kick things off real broadly and talk about neuromorphics in general, if that's okay. And then we'll work our way to your most recent work here. So what are neuromorphic chips, and how do they compare to the CPU chips that are in computers these days?
Right. So, as you were saying, neural networks are inspired from the brain. I mean, they are inspired by biological neurons and biological synapses, which are all wired together by axons and dendrites. And it's true that today, these neural networks are basically run in software. So they are lines of code in Python or whatever, and then they are binarized in a series of zeros and ones, and then they are sent into our digital processors, right? Like CPUs or GPUs, or even there are new ones that have been fabricated by Google that are called TPUs.
Huh.
And so this may seem all very good, but actually there are some limitations to doing that. And in fact, there are several problems. And the most clear one is a problem of energy consumption. So if we see neural networks as huge fit functions, where you have all these parameters, which are the synaptic weights, you see that when you want to have better performance, it's good to have more parameters, right? So people are to scale up these neural networks.
Yeah, a lot of these things are like hundreds of layers deep these days.
Yeah, exactly. So when you want to do image recognition, for example, you need about to have 10 to the 8 parameters. And this already is going to consume like kilowatts or even more. And if you want to scale these things up, which people are trying to do now, when you get to a number of parameters like 10 to the 14, then this is going to consume megawatts, and it's going to be super slow to learn, and it's going to be impossible to manage, basically.
So it's a real barrier to progress, I suppose.
Yeah, that's a real barrier to progress. And we could say, okay, maybe there's nothing to do, but actually when we look at the brain, you can say that the brain is a big neural network, and actually it's really huge. There are 10 to the 11 neurons in the brain, and about, these are orders of magnitude, right? But 10 to the 15 synapses.
Yeah.
And so, and it consumes only 20 watts, so like a light bulb, basically. And it can really learn in real time. It's quite fast, even if the individual elements are slow. So it means that we should be able to do better than what we do now with our CPUs or GPUs, right? So that's why it really makes sense to try to look at what is different in the brain, and can we try to copy it to improve the way we compute, basically.
You have a physics background, and you did your PhD on what's called the spin-torque transfer effect, which we'll get to. But how did you come to be? Did you originally have a concern with energy consumption, or was it through working in this field that you learned that this could be a benefit to using these techniques?
Yeah, it's by working in the field, actually, that I started to get really interested and understand how really the energy consumption was a huge problem, and that, maybe we'll come to that later, but that really physics and new nanotechnologies could help in the field. What I wanted to say first is that, in a CPU, there are many differences between the processor and the brain.
Right.
And so there are many different aspects. So some things are quite evident, So for example, in a CPU, everything is coded in binary, whereas in the brain, you can consider that the neural spikes are binary, but you also have analog coding because the synapses seem to be analog. CPU is 2D, but the brain is 3D. Also, in a CPU, everything is rather sequential internally and very synchronous. So you have a big clock, whereas in the brain you have a lot of you have dynamics. You don't have a central clock. Everything has its own rhythm and is fully parallel.
Oh, that's good, because I just interviewed Dean Buonamano about all the clocks in the brain and how that all works. So that's good.
Right. Yeah. Absolutely. Yeah. Okay, so that's one thing. So, but there are two other points that are very important when we want to think how we could make these neuromorphic chips and that we could benefit from. The first one is that you see in a computer today, every component is very high precision. Everything has to be perfect because you cannot tolerate any error.
Right.
Because if you have a switch between a 0 and a 1, it can really affect the final number that is coded. So you cannot, and this to allow this precision and this lack of error requires a lot of energy consumption. Whereas the brain seems to be working in a completely different regime, maybe at the thermal limit, where in fact neurons and synapses seem to be highly stochastic. And still they seem to be able to function, right, probably through the algorithm. So it's already one thing that can be, taken inspiration from in order to build a chip that doesn't consume too much energy, trying to allow for this stochasticity to reduce the energy that we need to bring to compute. But there is something that is even more important, is that the another really big difference, and where the energy consumption is very important, is that in a CPU you have really two different blocks. You have the memory block, and then you have the place where you do the processing, and they are really, they are specially separated, right? And so this
is like the von Neumann kind of architecture, right?
Yeah, exactly. And so this von Neumann architecture is really a problem for running neural networks, because you have all these huge number of parameters that you have to fetch in the memory, and then you have to bring them to the processing part where you do all these huge matrix vector multiplications, and then you have to put the result back into the memory, and so you need to do all this transfer of data back and forth, and this consumes really enormous amounts of energy.
Yeah, I like your analogy to cooking in the kitchen and having your supplies.
Yeah. Right, exactly. It's like a badly built kitchen, right? Where you have a table where you have your ingredients, and this is the memory, and you have to do the processing on another table that is like meters away. So that would be very inconvenient.
Yeah.
Yeah. And it's very different in the brain, because in the brain you have the synapses and neurons that are completely entangled, and it's really like the synapses are holding the memory for neurons. They are very close, and they are giving the memory to neurons, and like that you avoid this data transfer. And this is really where the economy of energy comes from. So having this massively parallel architecture where you have memory and processing in very close proximity. And so, I wanted to say that because for neuromorphic chip, the idea is actually the following, is to say, okay, but then if we want to have this memory and processing close together, why not, make, instead of coding everything in zeros and one and sending it to a CPU or a GPU, why not make physical neurons, layers of physical artificial neurons, and interconnect them directly with some kind of synapses that are really in between the neurons. So that's the main idea for building neuromorphic chips today.
You mentioned also the stochasticity, and that's, in the brain, we still don't really understand what stochasticity could be useful for. So it's a really still an active area of research, but yeah, to build that into the chip could be an important benefit as well. So you'll have to forgive me for my naivete in a lot of these areas, because I don't have that strong of a physics background. So you're going to be carrying me through this. So I'll appreciate it in advance.
Okay, I will try.
Yeah. So let's talk a little bit about just the different types of neuromorphic chips that have been tried and are being created today. Sort of the landscape of what this all looks like, because I'm ignorant of it. So educate me, please.
Okay, so let's try. So as you said in the beginning, as soon as the brain has been, let's say, modeled as some computer or some logic network, as soon as this has been done, I mean, people have been trying to build these kind of things, right? To make machines. So I mean, early, you talk about Frank Rosenblatt and Terry Sejnowski's attempts, but even in the 50s, Marvin Minsky started to make some kind of machine also. But of course, at this time, they were using the technology that was available to them. And so, I mean, they were using these huge, big elements. So, I mean, for example, the machine of Minsky had only 40 synapses, and it was a big thing already.
Yeah.
Okay. Yeah. And then after that, in the 50s, transistors appeared. So it was the beginning of our current electronics, basically, because this is a building block of the electronics today.
The digital age, I guess you could say.
Yeah, the digital age, if you want. And so this, on one side, gave rise to our computers today. But on the other side, it was a new building block for trying to make neuromorphic chips.
Huh.
And so already in the 80s, there is a very famous scientist called Carver Mead, who proposed to use transistors to make chips that are really directly inspired from the brain. And so his idea was to use transistors not as a switch, but in a regime where they are subthreshold and where they have this nonlinear behavior as a function of the input voltage. And he thought he could use that to imitate biology, because this is something that you see a lot in biology. And so he proposed and he built very beautiful and sophisticated neuromorphic systems like artificial cochlea, artificial retina.
Mm-hmm.
And this kind of chip, I mean, today are still developed. So of course, they are more and more sophisticated, and it's a trend that is going on. And the people who are working in this area are really, their goal is really to model and to imitate and understand the brain by building these chips.
Well, so that's in the 80s, but before that, so you've done some work with what are called Memristors, which are these little nano resistors, but they were invented in 1971.
Yeah, absolutely. There is this beautiful, it's a neural network by Widrow and Off, right? So I think it's called Adeline, and they used in this, it was a kind of perceptron, I think, and they used a device that they called, at the time it was called Memristor, not Memristor.
Oh.
Yeah, the idea was to say, okay, the information we propagate is the electrical current, right? And synapses need to be valves, analog valves for the information. So a good valve, a good way to modulate an electrical current is to use a resistance, basically.
Uh-huh.
And so they used some device that was big at that time. It was a huge thing also, called the Memristors, that was doing exactly that. So it was the first artificial synapse based on some modulated resistance.
Okay, and then sort of it's gone on from there and developed. But
yes.
You've touched on this just a little bit already, but what are the current challenges to developing these bio-inspired neuromorphic chips that can run in parallel?
So I would say there are two huge challenges. So if you want to make a very small chip, let's say really like 1 centimeter square, like approximately, and you want to fit in a lot of neurons and synapses, which is necessary to run some very useful computation. Then when you make the calculation, you see that if you want to fit in, for example, more than 10 to the 8 neurons and synapses, you need every device, every neuron, every synapse to be really small. I mean, the lateral dimension has to be less than one micrometer.
Mm-hmm.
It means that you need to make nanosynapses and nanoneurons, so you need to give them the important functionality at the nanoscale, which is already difficult, but you need to do that with a very good performance, because as you were saying, the brain is stochastic, but we don't really know how to use that into the algorithms. So we might want a little bit of noise, but not too much, and we want to have limited variability and to have devices that are persistent, that are not going to drift or degrade too much, and all this at the nanoscale. So this is really the first challenge. And the second challenge actually is once you have all these devices, you need to connect them together. And maybe this is the biggest challenge of neuromorphic computing because, as you know, the more interconnected the neural network, the smarter it can be. In the brain, there are 10,000 synapses per neuron, so it's enormous.
Yeah.
It means that every neuron has to be connected to other ones by 10,000 little wires in a chip. So this is really extremely complicated. And so I mean, we need to find smart ways to do this.
One thing that I am just completely ignorant of is how these, I guess we'll get into it, but how these chips are built at such a fine scale. You know, I picture little tweezers, but that's not how it happens. So, you know.
Okay. Yeah, I see.
Yeah. Well, maybe we can talk about the actual manufacturing later, but let's get into your paper and sort of the science that led up to this. So you recently published in Nature, of course, because that's the only place you seem to publish, Vowel Recognition with 4 coupled spin-torque nano-oscillators. All right, I love that title. So you set up this neural network physically, that is, using the hardware that we'll discuss, and you trained it to recognize distinct vowel sounds. And these were sounds from recordings of people saying different vowel sounds. So this is a sort of a proof of principle because it's kind of a small network, but you successfully trained a nano-scale spin-torque oscillator network to recognize vowels. So this is cool stuff. So we got to back way up, though. So what are Spintronics and why use Spintronics for bio-inspired computing?
So Spintronics is short for electronics using the spin of the electrons, basically. Yeah, so the idea is that you can get additional functionality by doing that. And to use this spin, what we do is that we combine, let's say, we send currents through multi-layers that are made of magnetic materials and non-magnetic materials, basically. So the basic component of Spintronics is called the magnetic tunnel junction. And you can see it as 2 very little magnets piled on top of each other and separated by a very, very thin insulating layer. That is a magnetic tunnel junction, yeah.
Yeah, a little sandwich with magnetic layer in between, yeah.
Yes, exactly. And why these devices are interesting? Well, first, they are today developed for making novel types of non-volatile memories. So they are used in a binary mode. So what happens is that so these little magnets can be seen as little compass, right? And when the needle points to the left or to the right, or this encodes the 0 or 1.
At some threshold, I guess, right? Between there has to be a readout of the actual. Yeah.
So actually,
angle,
when you can switch between these 2 modes by sending short pulses of current through the device. And then you can read easily because when the needle switch, the resistance changes basically between 2 different levels. So that's how it works.
So it's computing based on the spin of the electrons and being able to manipulate those.
Yes, and these devices can be made really, really small, like with a diameter of 10 nanometer. And so you can, there are already prototypes of memories using these devices, gigabits prototypes.
Yeah.
And they are built on top of a layer of transistors, so they are compatible with current electronics. So for example, why they are interesting in themselves like that, in this binary mode, they are already very interesting because they could be used to store a huge number of synaptic weights coded in the floating number, for example. You see what I mean?
Yeah. So we talked about the Memristors before, and those can be used as well. But I guess the issue is that the Memristors are too large to really fit enough onto the chip, and that's an advantage of these Spintronic components.
No, I mean memristors are really very similar in a sense because they can be made very small also, and so they can store multi-level. They are multi-level resistance. One memristor can be a synapse in itself. You don't need to use several memristors to code for the synaptic weights.
I see.
What Spintronics bring in addition, in fact, in more than that, is that it's very multifunctional. For example, this magnetic tunnel junction that I was describing can be more than just a memory. So, as I was saying, when you send a small pulse of current through the device, the needle can switch. But if you send the current constantly, the needle can start to rotate in a permanent way. Yeah, and it rotates at it can go from megahertz to gigahertz. And then when you measure the voltage across this junction, you get some kind of sinusoidal oscillation that is very fast. And the amplitude of the oscillation and the frequency of the oscillation is very nonlinear. So our idea was to say, okay, in deep networks today, a neuron has to perform some kind of nonlinearity. And here it means that we have some device that takes as input a current, that outputs an oscillation that is with an amplitude that is nonlinear as a function of the input. So it performs some computation. It's this nonlinear function. Since it emits a wave at gigahertz, this neuron can broadcast in its results.
So you call this you call it a nano-oscillator.
Yeah.
So we haven't talked about the torque yet. So let's build in the final piece here. So we talked about Spintronics and you just described how they oscillate and can be read out. Well, the full thing is called a spin torque nano-oscillator. So what's the torque?
Yes, I forgot to talk. Thank you for pointing it out. So when you send this electrical current through this little magnetic sandwich, so the current comes from a normal metal. So in average, it does not carry a spin. But when the electrons go through the first magnetic layer, they are going to get some spin. You say it's some kind of polarizer, so it gets spin polarized. So the electrons that go out, they are going to carry a spin, and this spin, they are going to transfer it to the next magnetic layer. And by transferring the spin, they make the magnet spin, right? So it exerts a torque on the other magnet.
Right, so it transfers the torque between.
Yeah, it transfers the torque, exactly.
All right, so we're all caught up here, so we all know how these things work now. And what you did in this paper, you set up a neural network, like I said. But actually, so you had work leading up to this. And if I understand this correctly, you have, in the past, you have used a single nano-oscillator. It was able to function as a neural network itself, one unit. Is that right? And if so, how did that work?
Yeah, so we wanted to first show that one oscillator was good enough to be used as a neuron and able to do some neuromorphic task. And since we had only one to start with, we used a trick that is called the time multiplexing. And so, in fact, this oscillator plays the role of all the neurons in the network, one after the other. That's what happens.
Oh, so it's in sequence. I see.
Yeah, so you go back to sequential computing, but this allowed us to benchmark our device on some kind of database. So we could do spoken digit recognition and show that we obtained very good results. So it proved that even if our neuron is very small, it can do good things. Yeah, that was the idea.
Okay, great. So yeah, and those were on spoken digits, 0 through 9, I guess. Is that right?
Yes, 0 to 9. Yeah.
Yeah. Okay, so fast forward to this most recent work. Let's talk about how the network was set up. Like how many units, and what was the input and output and all that jazz. Can you set us up here?
Yes, as I just said, you see these spin torque oscillators, they can emit waves. And what is interesting also is that so they are like, you can see them as some kind of radio emitters.
Yeah,
but
okay.
In fact, they also can act as radio receivers. So because they are the oscillation frequency and amplitude is highly nonlinear as a function of the electrical current or the magnetic field that is applied. They are extremely sensitive to incoming electromagnetic waves. And they are so sensitive that imagine you have two oscillators that run at different frequencies, but you put them close enough, they can synchronize. So they can mutually influence each other and end up in a state where they share the same frequency, even if originally they were autonomous. So in a sense, it means that they are radio receivers because they have their own wave, but when they receive another wave, they are going to modify the way they oscillate. And so we thought that we could use this nonlinear dynamical process for computing. Our idea was to say, okay, imagine you have the concept is the following. Imagine you have different layers of neurons, and that we want to make them communicate through wave. So the first layer of neuron is going to do a computation, emit a wave, and the next layer is going to receive this wave and modify its output as a result. And we thought, okay, how could we compute with that? And of course, there are probably many, many ways. I mean, all this needs to be invented, but what we propose in this paper is to say, okay, if the two neurons get synchronized, this is equivalent to having good communication between them. So it's like having a very strong synapse. And if they don't influence each other, it's like a weak synapse.
So in the parlance of like neural networks, it'd be like weak and strong weights between units as well.
Yeah. Yes, exactly. So, I mean, what is nice with these oscillators that in principle you can have billions on a chip, but in a lab we cannot control so many of them because of our equipment. So we started with we had 4 of them. So with 4 of these oscillators, we emulated the a layer of neurons, and we imitated the first layer of neurons using some microwave source that emitted waves. So we have 2 of these sources. They emitted a wave of different frequency and they sent it to this layer of neuron with 4 oscillators.
Okay, so 2 microwave inputs at different frequencies going into 4 nano-oscillating units that are fully connected by way of their waves.
Yes, exactly. And so these 2 microwave sources, the 2 frequencies, the 2 incoming frequencies were coding for the vowels that we wanted to classify.
And did you, I can't remember, so you have this audio of the vowel sound, and then was that transformed into the frequencies, or are the frequencies directly from the vowels? Okay.
Yeah, it was transformed and accelerated because our oscillators, they work at, in that case, it was 300 megahertz.
Oh, right, sure.
The frequencies of vowels are much lower, so so it was, we did some linear combination of the formants of the vowels.
Gotcha. And then how is the signal read out? How are the outputs read out?
Yeah, so what we did in that experiment is that in our lab, we plugged the spectrum analyzer at the output of our 4 oscillators, and we looked at their emissions. Mm-hmm. And so the way we wanted to compute, as I said just a little bit earlier on, we wanted to use a synchronization. So our idea was to use the different synchronized states of the oscillator, the synchronization to the input. So, for example, when a given vowel was sent, even if different speakers with different accents were pronouncing it, we wanted to have always the same synchronization configuration. So that, I don't know, I can give you an example. For example, we have these 4 oscillators, and let's say if you have the vowel O, you want always oscillator 1 to be synchronized to source B. There are source A and B, and we always want to have oscillator 1 synchronized to source A.
I see.
You see, and for another vowel, we would use another synchronization configuration.
I see. So and combinations between all of them as well.
Yeah.
Okay, so in what people of my ilk think of when they think of supervised machine learning networks, they use backpropagation to train the network, and that basically takes the errors that the network makes and then sends them backwards through the network and tweaks the weights between all of the connections in the between the units in the network in a way that nudges them closer to the correct answer. And you do that over and over and over, and that's the training regimen. So how does this nano-oscillatory network learn?
Yeah, so in that particular case, because we are just starting, so we did not really have synapses. The synapse is the coupling between the input sources and the oscillators. And so in order to allow learning nevertheless, we modified the frequency of the oscillators to learn, because this modified the way they would respond to the input sources. So if you want to make an analogy with classical neural networks, it would be quite similar to trying to learn by just changing the threshold of the activation functions or something like that.
Oh, I see. I mean, so what are the advantages of this network? I mean, this is going to be kind of reiterating what we already talked about. So I know that one advantage of using a network like this is just the energy efficiency. What are some of the other advantages?
Yeah, so of course we are starting very small, and here we don't want to say that the algorithm we used here is very interesting, or it was just a proof. I mean, it was just a proof that this was working. And and now we are much more ambitious. So we have all these. So potentially, you see, we could, because you can make gigabits. You can make arrays with billions of these elements. First, we are going to try to make synapses. So we have ideas to do that, and we would like really to make huge arrays of these oscillators, followed by synapses, followed by oscillators. So we want to do two things. We would like to show that we can run very classical deep learning, like using backprop on these networks. That's something we are going to try to do.
Oh, wow.
But also, because they are, as we said, you see, they are oscillators, they can synchronize. So we would like to see if we can, by using these features, we could compute more efficiently. We would like to see if by using nonlinear dynamics, which is something that happens in the brain, this synchronization process happens in the brain, neurons can synchronize in the brain. And so my belief that somehow it's useful for computation, and we would like to think how we could, enhance deep learning through this nonlinear dynamics. But for now, it's completely speculative. It's something that we need to figure out, and we are going to study this.
Yeah, so much in the future to do. That's awesome. So, I jumped the gun a little bit, but what happened with the network? Did it learn the vowel recognition sounds, or did it fail completely and you got into nature either way?
No, actually it did good. No, it could learn the vowels quite well. For such a small network, we could achieve like recognition rates of 85%. And a multi-layer perceptron with the same number of parameters would do approximately the same. So once again, we are okay. So
yeah, good. And there's a nice video online as well to sort of illustrate the network learning while the vocalizations are happening, the vowel sound vocalizations. So I'll link to that in the show notes. One of the advantages also of these nano-oscillatory neural networks, if I remember correctly, is that it reduces the number of parameters needed to perform at the same level. Do I have that right? And
Yes, we found that indeed, our network for the same number of parameters was doing a little bit better than a multi-layer perceptron with the same number of parameters. And we think that's because the way we built this network, the neurons in one layer are coupled to each other. And so when they synchronize to the input, they influence each other. And it's a bit like saying that they collectively take the decision, you see. And so what we showed through simulation that this coupling is indeed important to get a good result. Yeah, that's something we want also to think more in the future, is how to use these couplings inside one layer to enhance the computation.
It's got to be expensive to make these chips right now. How long does it? So I'm wondering what you're going to be doing next, right? So you had a 4 unit network here, and now you think, well, now I want to put, I don't know, 100 or something, let's say, on a chip. And how long do you have to wait for the manufacturing to take place?
Yeah. So for us, it's going to be a big step. So what we are going to do first is to make networks with hundreds of these devices. So this can be done by doing some homemade circuits, if you want, but integrating many of these devices. So this we can still do.
You mean like many of the like 4 unit networks, like connecting them together, or is that what you mean?
I'm thinking of, the next step we will do, for example, try to put, have layers of 10 neurons and some like 100 synapses and something like that. This, I think we can still do by ourselves in the lab by using a printed circuit boards and things like that. But then, of course, if we want to go to millions of devices, we will need support from industry because this is extremely costly, as you say. And so, we are starting to talk with people who can manufacture these devices because there are now many foundries who are starting to integrate magnetic tunnel junctions in their process for building really, big wafers. And so, so we are starting to see what is possible.
It's kind of frustrating that you're having to sort of wait for manufacturing to catch up,
Yes, but there's so much to think in between. You see the algorithm, how to connect. It's okay. We have things to do in between. So.
Yeah. You're not suffering from lack of anything to do. Well, so this is great. This is awesome work. So, sort of the summary is that you built this neural network using these spin torque nano-oscillators and successfully trained the network using a few tweaks and trickery here and there to transform sound into frequencies to inject in the network. But you built a neural network, a hardware implementation of a neural network. And I should say it's extremely stable. Isn't that another advantage of this type of network?
Yes. For nano devices, magnetic materials are very stable. So yes, that's important for learning because if there is some drift of the properties, then the learning cannot be achieved. And here it was okay.
Great. This is awesome. I'll point people to the paper, of course. So in our remaining time, do you want to just kind of open it up and talk a little bit more broadly? And can I ask you a few kind of broad questions?
Yes, of course.
So I'm curious how, if you communicate much with the machine learning community and the neuroscience community and what their take is on this. Are people excited? Do they not want to hear about it, etc.?
So, yes, we are starting to talk with people from machine learning and the computational neuroscience community. Yeah, so let's say, of course, for now, what we are doing right now is not really, is too small for them to be interesting. But
sure.
Now the machine learning community has really turned to try to adapt backprop and deep learning to hardware. Trying to reduce the precision of the weights. There are all these papers that you talked in your podcast about how deep learning could be implemented in the brain, which is some kind of hardware. So there is some link here to talk with people from machine learning, and also computational neuroscientists have always been very interested in neuromorphic chips because their models are very complex and they know they cannot run very well on CPUs and GPUs, and so they are very eagerly waiting for this kind of systems to scale up to run their models, right? So,
speaking of that, the current trend, it seems to be the current trend in deep learning network, is to continue building more brain-like features into these models. So there are people trying to build dendrites, for instance, into the units, like Blake Richards, whom I spoke with, and the further we progress, it seems like the more neuron-like features are being built into that. And I'm wondering if that's relevant for these nano-oscillators and how brain-like you can get or even want to get with them.
Yes, that's very, these brain-like deep models that are being developed are for us extremely interesting. because they are bringing deep learning closer to the hardware that is the brain, and so they are getting easier to run on our devices, closer to what we could run. So we are reading all these papers and trying to understand and see how we could maybe augment the functionalities of our artificial neurons and synapses, also to look more like what these models need. So yes, there is some kind of bridge here that we are working on, making this connection.
Yeah, I'm curious to see how brain-like, when does it stop? Because eventually you just model the entire brain, and that doesn't seem necessary. But who knows what features are really important and what aren't? I guess we'll find out.
Yeah, absolutely. Well, I must say that one of our objectives, of course, I think everybody in this community is fascinated by the brain, but we would be happy already if we, are able to build a small chip that can do something useful with very low energy consumption. That would be good already.
Oh, that would be great. Yeah, that'd be, that's why I said you're saving the world, out to save the world here. So,
well, not yet, huh?
Not yet. Well, hey, but you still have plenty to do in the meantime before you save the world. So these units, you talk about how that they last a long time. You write in the paper, so they're stable and they're hardy. Eventually, in let's say an AI system, you're going to have to replace a unit, right? And these units respond differently to different current injections. But when you have to replace a unit that wears out, is it possible, because this unit has been trained, right, with the essentially training weights, what analogous to training weights, over time, can you then replace that unit with a new one that holds the same training? Does that make sense?
Yes, but that would be complicated because indeed we do it in hardware, so we cannot replace a device. So, but what has been shown is that what is very nice with the neural network is there is some kind of a bit of redundance. So you can lose neurons up to a few percent and synapses even more without degrading too much result.
Right.
And if we want to avoid that, what we need to do is to build in this redundance. So have more neurons than necessary at the start, so that we can rewire if we need. But then you would need to retrain a bit, of course.
Oh, so more and more brain-like, indeed.
Yeah.
So, so far we've talked about using what's known kind of in neuroscience, and you derive inspiration also, I guess, from artificial neural networks when you guys are considering how to proceed. I'm wondering if there's anything if you've thought about how these nano-oscillators, if they can transfer any knowledge into neuroscience. Can we learn anything about the brain using this technology?
Yeah, that's a good question. I would love to say yes, but I'm not sure. I would. It would be great because, of course, by trying to build something, you always learn, right? So I hope we will learn something. What we try to do is each time we make a small prototype like we did is to get some lessons from it. So, for example, when we made our first experiment with the time multiplexing with only one neuron, we found out that, people always say, in neural networks, they are very noise tolerant. So noise is okay. But in fact, in a nano device, noise can be very high. And in fact, we learned that it's okay to have a little bit of noise, but not too much for it to work. So that's something we understood at that point. And so each time we try to learn something, right? And so I don't know if what we learned for these oscillators could be applied to the brain, but maybe there are some links,
Yeah. Well, when we were talking earlier, and you're talking about how sensitive they are to fluctuations. Mm-hmm. I was kind of picturing, my mind just goes straight to a robot for some reason, but, if I just have my microwave gun, can I just deactivate the robot, But I guess they'd be built into little black boxes and shielded from the radiation.
Yeah, absolutely. Yeah.
Okay. So this seems like hard work, Julie. Could you tell me about something that you failed at or got rejected from or were just wrong about sometime and how you moved on from it?
Yeah, I don't know. I've been like everybody. I had so many failures and did things wrong. One thing that happened to me is that when I wanted to get this project funded, and I tried to get a European grant. So I wrote a project and it went out to many referees, and then it was rejected, and I got the referee reports. And one of them was saying, okay, this Julie Grollier, she has all this idea, but she never does anything, you know? I was really angry at that, but at the same time, sometimes it's a bit true. I tend to dream and figure it in my head, and then maybe don't do it enough. So I said, okay, this time I'm going to do it, right? And so, yeah, that's what I've been doing these last years, and it worked out in the end. So
you've become a woman of action. That's actually one of the reasons why I decided to go to graduate school, because my sort of default is to be a dreamer and not do, and So I kind of forced myself into action by going into graduate school, you know.
I know what you mean. Yeah.
Yeah, and I learned how important action is, and sometimes I preach a little bit on the show, trying to prod people into action. And I think my audience doesn't need any prodding, so I don't really need to preach. But that must have felt terrible.
Yeah, it a bit. But then, you see, I could overcome it.
Yeah. Well, so you're doing stuff, but you are a dreamer, and I'm wondering if there's something that you believe, because it's just impossible to predict the future. We're terrible at it. But is there something that you believe that'll come out of the interface of neuroscience and artificial intelligence and maybe physics that might be a little out there?
My dream is really to see, one of these big artificial neural networks that produce something really, amazing, like, computing through nonlinear dynamics with very low energy consumption. And that would be really great.
I like how you often start your talks with the energy consumption, and it really is a huge problem that I think goes under the radar mostly.
Yeah, because there's been all this progress. So GPUs are doing better and better. So people might have the feeling that it's going to go on, but actually there are really some limitations that we are going to hit soon. And so we need to think about that now, I think.
Julie, je vous remercie. Is that?
Merci beaucoup.
Oh, thanks for talking with me today. And this is really fascinating work. Keep up the good work and keep up that action so that you don't get those reviews again.
Yeah, thank you. Thanks for the advice.
Brain Inspired is a production of me. You can support the show through Patreon for a trifling $2 or $4 per month. Go to patreon.com/braininspired or go to the website braininspired.co and find the red Patreon button there. Your contribution will help keep this show going without any annoying advertisements like you hear on other shows. To get in touch with me, email paul@braininspired.co. The music you hear is by The New Year. Find them at thenewyear.net. Thank you for your support. See you next time.
The